Hi, this is Professor Cummings, and I have a video here where I wanted to tie in a lot of the curvilinear motion or the rotational motion, rotational analysis that I've been going through these last few weeks, end with mechanical design or back into mechanical design. Now, we did some example problems that tied into it, but now I'm going to be a little bit more explicit with this video, and I'm going to be speaking specifically on gearing and velocity ratios, or mechanical advantages. Now, the thing that ties this subject together, or why this is tied to your kinematics, is because of this equation here. The velocity, tangential velocity, is equal to the radius times omega, which is your angular velocity. Now, again, I've got the title here is tangential velocity versus angular motion. And you're going to see the same slide that we had spoken to just a few videos ago. So your tangential and angular velocity are related through the radius of rotation. All right? So there is a relationship between the two. And as you can see, when it comes to gearing, we're talking about gearing itself. You can see that it is proportional. Now, you saw that in some of those example problems. Now, the example problems just use that as to illustrate the equation. Now we're going to start seeing how it can be applied to a gearing system. Now, a few things about gears. They're there to change speed. They can change the direction of motion, and they also can transmit and utilize torque or forces. And that's the whole purpose of them. And you can see that they allow people to amplify or reduce both speed and force, or torque in this particular case. But let's look at the different configurations and how this equation does apply. So again, you have the equation where we have a common tangential velocity. Now, if we just look at say the green gear, gear B, you can see it's got a rotation to it of so many, whatever omega is, and the tangential velocity would follow this equation. V equals R times omega. So whatever the radius is on this, you would be able to calculate a tangential velocity. But when gear B is enmeshed with gear A, you notice that they have, they're rotating in two different directions. The teeth are part of the engagement, and they share a common tangential velocity. And what you can see from this equation, if we were to calculate the tangential or the angular velocity between them, or in this case, the angular velocity is what I'm showing in this one. What you can see, let me get the point of the pen out, is that with the common tangential velocity, the angular velocity is inversely proportional to the radius. Now that's going to be important as we start to move forward. That this angular velocity is inversely proportional. So what is happening is, the speed of one, the angular speed of one, is causing a slow up or speed down, inverse proportion to the radius of it. In this particular setup, if gear B was the driver gear, it would be causing gear A to go at a higher speed with itself in proportion to that radius. But it would have a common tangential velocity. Now, you can see the same thing with belts and pulleys or chains. The sprocket on your bicycle would be a really good example. They have a common tangential velocity in that belt. Common tangential velocity in the belt here, but different sizes. And you can see that the angular velocity with the common tangential velocity, the angular velocity is inversely proportional to each respective radius. And the same deal applies as this one rotates. The smaller one, pulley B, actually rotates at a higher speed. So if you've got, if this is the driver, you're going to speed up the system. If this is the driver and this is output, it'll slow down the system. Now, you also have another way that gears can be engaged, and this is where you have a shared axis. And the shared axis have a common angular velocity, Both of these, if you look at just these two on the compound gear side, they have a common axis, so they have a common angular velocity. So here omega is common, and the tangential velocity is directly proportional to each radii. So the tangential velocity are different here, but it's directly proportional to the radii. And this, again, with the output gear, this smaller gear has a common tangential velocity. And this tangential velocity is actually different than the smaller one. So there is a tendency to take the, actually slowing down the system. It actually is here is to slow this down, to slow that output. So the rotational velocity of the output gear is being reduced if this is being driven through this compound gear. But now let's look at other things this gear, like I just spoke totally in terms of velocity. There are other sides to gearing, and one of those is dealing with torque. And torque is a measure of how much force acting on an object causes that object to rotate. So here you have, the force. The example here is a torque wrench. One is 1 foot, hand is at 1 foot, and the other one is at 2 feet. And saying we're going to assume that the same amount of force is being applied, you would get more torque being out at the 2 feet point on the torque wrench. You think of that as a lever or any other mechanical device. The further you are from the fulcrum, the more of the torque you're going to be able to generate, and that we'll move on to what that is called. But that's your goes into your mechanical advantage. Another thing I want you to look at that is how does it apply to gearing? Here you have two different gears with all the notation all over it, but you got two different gears. And, one is clearly of a different radii of the other, right? You got two different radii between these two where their center of rotations are at. You've got a common, area where they mesh up, and that is known. Where they meet is your pitch circle. There we go. That is the pitch circle. So right here, that is your pitch circle for the big gear, and here you have your pitch circle of your smaller gear. This is where the forces are actually transmitted. You got your line of action that intersects here. Your line of action, the pressure angle, and that's based on the shape of the tooth called the involute. But right in here is where the tangential velocity as well as the tangential force between the gears are being shared. So there's the common force that would be the equivalence of the hand on these torque wrenches, and the distance to that center of rotation is what's being generated. So you've got a driver, some sort of driver that's generating a torque off of one gear and transmitting it to the other. And the amount of torque you're going to get through that rotation is based around the radius of the gear. So you can see the torque is directly proportional to the radius. And that W sub T in gear design, that is just the notation for force. There's a tangential force that aligns with the tangential velocity. So the equation looks more like this in certain applications, right? There's your tangential force, and that's your radius. So instead of gearing, the product of the tangential force and the pitch radius is how you calculate the torque. Now, to give you an idea, that is just the tangential force. When you look at a set of gears just diagrammed out, you can see that the tangential force is driving on the gear teeth right here. You do have a radial force, and you have a normal force, which is the resultant between the two forces. And again, it goes along the line of action. So now, keeping that in mind, so we've talked about velocity, how fast the gears are going to turn. Now we've talked about the ability for a gear to transmit torque or forces. So now, how does this measure? What's the point of it, and how can we speak to it? Well, we speak to it through things called the mechanical advantage, which we talk about with all machines. But velocity ratio is what you're more likely to hear people use when talking about gearing systems. So the velocity ratio is the ratio of the number of revolutions of the driving or the input gear to the number of revolutions of the output gear. So it is a ratio. It's a ratio between the two gears, and it's based around, here we have the number of revolutions of driving and driven, or input and output, in a unit of time. Now, there's a few things about this sentence that this definition I want you to keep in mind. The number of revolutions is based on a few things. It can be based on the radii of the gear, what the radius of each gear is. It can be based on the number of teeth of the gear. Again, assuming the gears have the same diametral pitch. It can be based on the overall diameter of the gear, which, is just tied right to the radii of the gear. And it could be based on things like knowing the actual velocity, usually the rotational velocity of the gear, or the rotational speed, which is just another way of saying, the RPMs of the gear. But, so there's several different ways to calculate it, but for all intents and purposes, the calculations that we're going to worry about right now is this lowercase n, which is rotational speed in RPMs of the input versus the rotational RPM of the output. And when you start going outside of this, again, that fits this definition, the number of revolutions per year, again, per unit time. Or you can look at it in, again, the ratio of the number of teeth, which would actually inverse the equation, but they still come out to the same ratio on the same number of teeth, assuming that they have the same diametral pitch. And the diametral pitch is that's the teeth per inch. And there are several reasons why it's important to keep that diametral pitch beyond just the calculation. There's really application issues, there's binding issues, there's noise issues. But, for our calculations to work, we need to assume that the input and the output have the same diametral pitch, the same number of teeth per inch are engaging. Now, when you look at the mechanical advantage, it's the same when you learned back in 8th grade science class when talking about simple machines. A measure of the force amplification achieved by using a tool, mechanical device, or a machine system. So again, that's just the mechanical advantage. And we can measure that typically with gearing by looking at the torques. Again, now we're looking at the torque output versus the torque input, which again is just, has an inverse relationship between these two, between the velocity ratio, this portion of the velocity, this calculation of velocity ratio. And that's going to become important as we start to move forward. Now, another element of gearing that's going to be important is how can they be designed into the system? Now, you've calculated a velocity ratio, or a velocity ratio that you need. You want to, amplify the velocity of a motor or address the torque some kind of way. Now, you got to make sure your gears actually fit. This is why diametral pitch another reason why diametral pitch is important. It comes into mounting the gears, or gear installation, right? And in order to do this, you need to know the center-to-center distance. And the center-to-center distance is just what it sounds like, the distance from the center of one gear to the other. Making sure that you do have the right ratio of diameters, right ratio of teeth, in order to get the output that you want. You're going to inevitably end up with a certain center-to-center based on those two ratios, based on that ratio. And that impacts whether you can mount the gear together or not. So again, you can see that these two gears, that diametral pitch, this is where the forces all hit with each other, still matches right in here. So these are well-mated, theoretically well-mated gears. And, you need to know, based on these, assuming you have the same diametral pitch, that this center-to-center distance is going to work out. And again, there is a right calculation to this, and it's that theoretical center calculation. Theoretical center, or the center-to-center. It's based on those two pitch circles. So pitch circle of gear 1 plus the pitch circle of gear 2 divided by 2. And that will land you, right in where that theoretical center-to-center should be. And you can design your mounting conditions from there. And again, assuming that your diametral pitches are the same, you will be able to calculate a proper velocity ratio with that. Now, let's just apply this a little bit. Speed and torque, or speed versus torque. Like we looked at velocity ratio calculation, we looked at mechanical advantage relationship. And if we just look at rotational speed, we just strictly look at rotational speed as our primary way we're going to calculate this, as well as, say, the number of teeth and the torque, we can start to see a really consistent relationship between the rotational speed and the torque, how they tie together. When your speed decreases, the rotational speed of your gearing system going from one gear to the other decreases. So if you have a high speed input gear and you're getting a lower speed on your output gear, you're going to see a decrease in the torque, right? And you can calculate this well before you even start to build anything. This is part of your calculation. Again, assuming the diametric pitch is the same, and you will also be able to use your teeth, the teeth on both sets of gears, to also find this. Now, when would you actually use that? Why would you want your speed, your output to decrease to get that extra torque? Well, this is one good example. Trying to go uphill. And this is showing a person doing it, but this could also be a car, an internal combustion engine, or an electric car going uphill. Your gearing system you'd want to be able to decrease, or where your primary concern is increasing that torque to carry all the extra load up that hill, which means your RPMs for your output gear is going to go down. But the torque starts to increase. Now, what about when you're trying to increase the speed? Right? So you have a speed increase where you're going to see a decrease in torque. And again, if you remember and think about the radii of the different gear, or the number of teeth of the gear, and that key equation, velocity is equal to R times omega, that also rings true, right? And where would you apply that? Well, again, this is riding a bicycle on a flat ground. You're not necessarily moving a load or your weight's not working against you. So you don't really need the high torque, but you do want a high speed. So your input, which is your feet, and your output, which is the sprockets on the back in this particular case. But the same could be applied if we were looking at a transmission system. Your speed goes up, the amount of torque you're generating goes down. This is also why you use your lower torque in your car when you're dealing with a situation where you need to be able to grab the ground a little bit better. So let's look at this calculation is actually being used. So if we look at this and we take into account this condition here, we've got a load, we're trying to go uphill, we're going to actually try and increase our torque, which means our speed is going to decrease, or maybe we've got a motor that is higher than the application that we need, and we need to lower that RPM down. So we're looking at a situation where we can decrease the speed, which will incidentally increase the torque on the output. You can have a system like this. So here, you've got a driver, which is the smaller gear, driving a significantly larger gear. That's the driven. So what you can think of this as is that in the same unit of time, the amount of time it takes this small gear to go one rotation, this one is only gone part way. If this is twice the size, twice the number of teeth, then this the one rotation of this gear generates half a rotation of the big gear. And half rotation the same unit time means half the velocity, half the angular velocity. So if we wanted to calculate the velocity ratio, we could do that based on the teeth itself. We could also do that based on the radii, or the RPMs. But teeth is always something you can count. So you can look at it, the number of teeth in the driven versus the number of teeth in the driver. It gives you 28 to 14. Assume there's 28 teeth. And 14 teeth, you end up with a 1 to 2 or 1 to 1/2. If you look at it as just, how many times this is turning, but 1 to 2 velocity ratio. So you're reducing your speed that much, and you're also increasing your torque. So if we had a motor that was 100 RPM at 10 foot-pounds of torque with this sort of system, that is the driver hooked up to that smaller gear, you'd end up with 50 RPM and 20 foot-pounds of torque. Now let's look at the other situation. Let's reverse those same two gears and put the motor onto this one, on the larger gear, the one with 28 teeth. So the driver and the driven now has 14 teeth. What we're going to do is we're going to increase the speed. As this goes around the driver goes around one time, this one is now being driven twice. It's going through 2 revolutions. And again, assuming the same diametral pitches per inch, teeth per inch, excuse me. If we look at that in just calculation to our velocity ratio, driver to driven, you end up with 14 to 28, which is 2 to 1. So if you have a motor that has 100 RPM and 10 foot-pounds, you hook it up to this system, on this is the driver, you're going to end up with the driven giving you 200 RPM, but you're going to lose on the torque, which is going to give you 5 foot-pounds. All right. So this is Professor Cummings, and I want you to go ahead and either like the video, leave any questions or comments down below, and again, thanks for watching, and hit the like button, share the video with people who might need this, and I'll talk to you soon.